Okay, today we're going to be talking about Bluetooth Low Energy. So for this lecture, I want you to understand just what Bluetooth Low Energy is, BLE, and how it differs from Wi-Fi. So throughout this lecture, we're going to be thinking about, well, how did Wi-Fi do this differently compared to Bluetooth? So I want you to be thinking about that. Before we get to that, a question for you that I'd ask in class if you were there sitting in front of me right now is, how would you go about designing a super low power protocol? So we've talked about this idea of these knobs that you can turn to change the data rate of a protocol, and what Wi-Fi has done to increase its data rate throughout time. So maybe the opposite question would be like, well, what would you do differently instead of increasing the data rate? What would you do to lower the power of a protocol? So I think if you would pause your video and think about this for a while, that'd be a good exercise. Just think, what would you do differently? What I would do different, and there's no real clear answer, it just depends, is I think not having a high data rate. Something high data rate, it means a lot of transmissions, a lot of energy going out. So having a low data rate, having a low transmit power would be another way to lower your protocol's power. So Todd, and when he came and talked about how you can lower the transmit power of an access point, Wi-Fi access point, to reduce its range. Well, if you lower the transmit power of another wireless protocol, it would reduce its range, but it would also reduce its power. A protocol that would have a lot of sleeping would be a good one, meaning you could put the device to sleep. You don't have to have the radio always on for it to work properly. A device could aggressively go into sleep and then wake back up and still work. So that would be important. Maybe less obvious answers would be, making the protocol simpler. Simpler usually means more efficient, not always. Making the protocol asymmetric, that's kind of an interesting idea. What I mean by that is that maybe some device like an access point or a controller or gateway, whatever you want to call it, would take care of more tasks for you than the device that you're trying to save power on. So making it asymmetric would be another example of making a protocol more efficient. And then, so the next question for you is, what do we already know about Bluetooth Low Energy? Sorry, just Bluetooth in general. We've talked about it throughout class. You've seen different parts of it. You've used it yourself, I hope, I imagine, with Bluetooth headphones and just keyboards. And there's a lot of Bluetooth around. Your smartphone has Bluetooth. It's talking. So what do we know about it? Well, we know it was a question on a test, a homework, was how that it uses frequency hopping spread spectrum. So that's one thing you should know already, that Bluetooth uses frequency hopping spread spectrum. You might also know that it's low data rate. You're not sending a lot of data through your headphones to play the audio. They have limited range and it's low power. So those are some of the key factors of Bluetooth. So like I said, we know that it uses frequency hopping spread spectrum. So my question for you is, what is the benefit of frequency hopping spread spectrum? Make sure you remember that benefit, because that plays a role into why Bluetooth uses this. Okay, so let's now talk about Bluetooth Low Energy specifically, or BLE. So it's part of the Bluetooth specification, Bluetooth 4, but it's not the same as Bluetooth. These are different things, and so you got to be a little careful about that. Typically your headphones are like a smart speaker is using Bluetooth 4, whereas Bluetooth Low Energy is slightly different. It was introduced in 2010, and it's actually hugely popular. So for such a young protocol, something like Wi-Fi was around for quite a bit of time before it actually gained traction. Bluetooth Low Energy, right out of the gate, as it got introduced, was used pretty heavily. So let's talk about its limitations. As we said, it's a low data rate protocol, so its maximum throughput is 1 megabit per second. That's theoretical. I've actually never seen that transmits that fast, but in theory it could support 1 megabit per second. But in actuality, you kind of kill all the battery savings you might get, and so it's much lower than that. And the range is 2 to 5 meters. It depends. You could have it go 100 meters if it's line of sight, or there's so it's hard to give an exact amount. But the idea is it's supposed to work within 2 to 5 meters, kind of rough size of a room, or large room or something like that. So there's two ways of communicating using Bluetooth Low Energy, and this is different. I mean, Wi-Fi, there's no two ways of communicating, but with Bluetooth Low Energy, there is two different ways of communicating. One is through what they call connection list or broadcast, and then one where you have connections. So let's first talk about the connection list idea here. So calling it broadcast, advertising it here. So in this case, there's two entities, two different devices. There's the broadcaster, the device that's sending out what we call advertising packets periodically. And it's just sending out, not sure what's going on, just sending it out periodically. And you got observers, and these are people that are looking for these advertisement packets, and they receive them and do something with it. So communication is just in one direction, typically. You have a broadcaster sending out information to observers, and observers are collecting that data and doing something interesting with it. It's severely limited. Like I said, it's only one direction, but it's also only 31 bytes of payload. So it's not meant for data transfers or really that much meaningful communication. It's really just meant for advertising, for broadcasting something, capabilities or other things. So we'll get to a use case in a second. But one thing I do want to highlight here is that there's no built-in security to this. All data is sent in the clear, so to speak. There's nothing stopping you from adding security in the actual data itself. You know, you could encrypt the data and then send that data. But Bluetooth Low Energy in this mode does not provide any security for you. And so example of this is what we call iBeacons. iBeacons is Apple's invention. Google has this same thing called Eddystone, but it's the idea of these devices, these really low power devices that just send out beacons messages to people. And so what you typically see is, for those of you that have iPhones, maybe you've seen this and have the Apple app installed. It's when you walk into Apple Store, it knows you're in Apple Store, because in the Apple Store they have these iBeacons that are transmitting out, and your phone is looking for that, or particularly your app is looking for those iBeacons and says, oh, I see this iBeacon. Now I know to prompt the user to open up the Apple app or to connect to Wi-Fi or something like that. And how it works underneath is actually quite simple. It's just broadcasting out a unique ID. It's just sending out ID, and your smartphone is just going to receive that ID and look and say, okay, well, does the app care when I receive this ID? What does it want me to do? And it does something with that information. So it can be used, iBeacons I know are heavily used for like location tracking within your home. You know, where GPS might not work is you can have iBeacons in different parts of your house, and when your phone sees an iBeacon from that device, sees an iBeacon of a certain ID, it knows now it's in a certain room or part of your house, and so then it can send that up to a server somewhere, to the cloud, say, okay, now Phil's in the basement or Phil's at the front door or something like that. And so it's a way to track someone much more closely than you could with like something like GPS. That's typically what they're used for, at least in home automation standpoints, but they could be used for anything. A grocery store could use it. But the important thing is that the app is what controls it. The smartphone is receiving them. It's the observer, and it's doing something with that information. The broadcaster doesn't know if anyone's around or not. It's just constantly sending out these messages. And these broadcasters are actually quite cool. You can buy them for like less than $5 in the little coin cell powered device, and you just put them anywhere. They're fun to play with. Okay, so this is the topology. I've alluded to this already, but you have this broadcaster sending out information in one direction to all these observer devices. So my question for you is there anything like this in Wi-Fi? This idea of sending just data in one direction to these devices that are listening, and another device that's not listening, just sending out this little bit of information that's not encrypted. No, there's nothing like this in Wi-Fi. Nothing technical from stopping it from happening. It's just Wi-Fi is not designed like that. I don't know exactly why they didn't do it. My guess is just for historical reasons, that Wi-Fi was designed to be like a connection, to be like you're physically connected to the internet or to a network. And so it didn't really make sense to have this kind of functionality built in. Bluetooth is a much newer protocol, and so they designed specific for these type of use cases, and so it had these features built into it. Okay, so that was the first type of Bluetooth kind of topology with the connection list. Now let's talk about the connections, and this should be much more familiar to you because this is how Wi-Fi is in terms of its connection based. So there's two types of devices again. There's a central and peripheral. The central node is the one that's advertising, scans for connectable devices to start a connection. And the peripheral is sending out advertising packets, and it accepts incoming connections. So it's kind of interesting. You could imagine almost that the central could be like our access point in a Wi-Fi network, and our peripheral could be a client or a station, is the term we use for Wi-Fi. But it's kind of different in that the central is looking for people to connect, and the peripheral is advertising. And Wi-Fi, our access points are advertising, and our clients, our stations are connecting. So it's similar, but you're starting to see some differences in these type of networks and why they're designed like that. And think for a little bit why that would be. Given the constraints of Bluetooth, that is low data rate and low power, it makes sense that the central would be the one that's searching, because centrals are typically well provisioned. They're the ones that have a big battery or connected, and the peripheral is the one that's got a low, a really small battery, and so it's going to send out advertising packets as it sees fit. Maybe it sends out one advertising packet a day. That wouldn't make much sense, but one advertising packet an hour or every minute, whatever makes sense for its battery usage. Whereas a central is the one that's going to use its all battery to search for it. Okay, so here's the topology for that. Once again, pretty simple in terms you got the central node that all these devices are connected to, and the data is now bidirectional at this point, and it's also encrypted. So that's saying that now this is built into Bluetooth Low Energy. It's now encrypted, and there's this this ability called this generic attribute profile, or GAT it's also called, and we'll talk more about that in terms of how Bluetooth organizes its data, because it's very opinionated on how it organizes its data. So, but the central controller controls all the communication. So is once again my question, let's compare this to Wi-Fi. Is there anything like this on Wi-Fi? Like I've already said before, yeah, this is much more similar to Wi-Fi. Wi-Fi is all about connections. You can only be associated with one access point, and you're connected to it. And it's as if you're plugged into it, and all data is bidirectional and encrypted. There is a slight difference, though, on who's listening to who connects to who controls that. That's where the difference is with Bluetooth Low Energy. And the cool thing about Bluetooth Low Energy is that you actually can mix and match all these different things. That you could be both a peripheral and a controller, and you could be observer and broadcaster, all these different things. You can mix and match. You can even have Bluetooth Low Energy and Bluetooth, regular Bluetooth all together, and so you can make for some really interesting topologies. I haven't seen this very much. It's possible in terms of the spec, but I don't feel like it's usually widely deployed, these kind of mix and match topologies. Okay, in terms of the physical layer for Bluetooth Low Energy, there's 40 channels in the 2.4 gigahertz range. And this range should look familiar to you because it's the same range as Wi-Fi. That hopefully you already knew that from the spectrum analyzer lab, where you looked at the spectrum and you saw Bluetooth Low Energy hopping around, and you also saw the Wi-Fi on certain channels, and so that you should already know that. Each channel is only 2 megahertz, so these are really small channels. Wi-Fi is 20 megahertz, 10 times more, but Wi-Fi also sends data a lot faster, and it's designed to send data a lot faster, whereas Bluetooth is not designed for that. Bluetooth Low Energy, it's just 2 megahertz channels. But what's interesting is that there's 3 channels that are used for advertising, and the rest are for data. So think about that. Why would there be certain channels set aside for advertising? So let's think of Wi-Fi for a second. Wi-Fi, there's no concept of advertising, right? Well, there is. Sorry, I correct myself. There is through beacon frames, but there's no set channel or place where that happens. Wi-Fi just advertises where it's also sending the data. But Bluetooth Low Energy has this idea of, I'm going to have certain channels designated for advertising, but the other channels are going to be used for data. So think about why you would need to do that. Why would you need a rendezvous point? And it has to do, as a hint, has to do with what spread spectrum techniques it's using, the frequency hopping spread spectrum technique, and because it's pseudo-random. So think about that, and that will be a homework question for you to answer that. So here's the different channels all laid out, what frequencies and what channels are designated as advertising channels. Okay, I guess I've been doing this as we talked, how this compares to Wi-Fi, in terms of the channel size, not having certain channels set aside for advertising versus, advertising on the channel you're actually on. So I think we've covered this and how it compares to Wi-Fi. Okay, so addresses. So this is now, we're talking about more of the MAC type of things. How do you identify address, devices in Bluetooth Low Energy? So the 48-bit addresses. So same as a MAC address. And there's two different actually types of addresses. There's static addresses, so much similar to our MAC addresses that we use to transmit data on Bluetooth, Wi-Fi and Ethernet. But they have this extra type of address. They call them resolvable private addresses. These are addresses that change randomly to hide the identity. So that way I can't just plug in a Bluetooth low energy sniffer, in our classroom and just sniff and look for your MAC address, for your Bluetooth Low Energy address. I could potentially, stalk someone by doing that. And so that's a big security vulnerability. So they've added this ability where it'll randomly change its ID so that me not knowing your key to randomly produce that, would not know if it's the same device or not. Okay, so data organization. This is a very important part and a huge difference between Wi-Fi and Bluetooth Low Energy is how data is organized in Bluetooth Low Energy. So there's three kind of tiered groups of entities. There's a profile, the highest thing, kind of the application, and then there's the service and characteristics. So profile, like I said, it's the application. It's the main thing. You have one profile for a device. And each profile has kind of multiple services. And a service is what you think it provides something. It provides a service for you. So one profile can have multiple services, and then a service can have multiple characteristics. Characteristics is the fundamental piece of data that you actually read and write from. And the semantics of Bluetooth Low Energy is very interesting in terms of you literally you read from that characteristic and you write to that characteristic, or you get notified by it. So it's not a socket abstraction, which what we're familiar with in terms of, I'm going to take this data, I'm going to send it on a socket, and I'm going to receive on that socket. They chose a different abstraction with Bluetooth Low Energy in terms of we have these characteristics and I'm going to write to it as if it's like a file, and I'm going to read from it. And under the hood, what's happening is Bluetooth Low Energy messages are being sent, but from your perspective, you're just reading from it or writing to it. And so the characteristics are where actually data gets created or produced. So as an example to help you I'm talking about is that maybe you would have this profile of a heart rate monitor. So you have some device, it has a profile for a heart rate monitor. It could have multiple services. So example would be the actual heart rate itself, monitoring part of the device. And the other service could be metadata, device specific data, things that tell you information about the device. And then the characteristics, there'd be maybe two characteristics for the heart rate service. One would be the actual measurement itself, so the rate of your heart's pumping. And another characteristic could be the sensory location on the body, so where it is on your body. And each of these characteristics, I didn't mention in the previous slide, some of them can be read or write only, or read and write. So you could imagine that maybe heart rate measurement is read only. You can only read from it, you can't write to it, but a sensory location is something that you can read and write to it, because when the person moves the sensor to somewhere other part of their body, you can update that. And then other characteristics might be the manufacturer name, and this would be under the device information service. It could be the manufacturer name, the model number, firmware version, whatever you might think of. And of course, like I said, there could be more services and more characteristics. These are just some examples. Under the hood, what these characters and services look like are UUIDs, these random, uniquely identified IDs. In Bluetooth Low Energy, it identifies many of these characteristics for you already. So let me click on this link. You can see all of these characteristics that have already been defined for you. Something like age, altitude. I mean, it's a huge list. Goes on for a long time. Lots of things that you think of. So if you're going to design a sensor, Bluetooth sensor or device, most likely a lot of the characteristics you care about are already here. So you don't actually have to define any new characteristics. You can just use this define characteristic for you. So let's click on one of these. Let's do latitude. So it shows you right here information about it, what kind of format it needs to be in, mandatory, and other information like that. So let's go back to the slides. Okay, so there's these Bluetooth Low Energy characteristics that have already been defined for us, but you can also, of course, if you need to, define your own custom characteristics if you wanted to for your own type of data. Like I said, characteristics can be read, write, or notify. I wanted you to be familiar with this term a little bit. This whole idea of how data is exchanged and this idea of characteristics is called the generic attribute profile, or GAT. So this is a common term you'll see when you start working with Bluetooth Low Energy devices. And it allows for different devices, different vendors and manufacturers to kind of have a common language to talk to each other, so that in theory I could have one app that measures heart rate, and I could use lots of different devices because they all follow the same kind of scheme for Bluetooth Low Energy, and so it allows it to be interoperable. This is just a visual representation of what it looks like in terms of you have the service characteristic and there's this descriptor for the characteristic. So let's talk about how this Bluetooth Low Energy data is organized, because it's very opinionated, right? It's got a very specific format to it in terms of characteristics and how you read and write to it. It's really a different abstraction than we've seen so far. So my question for you, is there anything like this in Wi-Fi? A follow-on question that would be, why does Bluetooth Low Energy have this? Why is this such a big departure from what Wi-Fi has? Now, Wi-Fi does have a certain amount of structure to it, right? Not inherent in the protocol, but in terms of the application, the stack. We have the Wi-Fi, and on top of that, things like network with IP and transport with TCP, and even application with things like HTTP. So that there is structure to the data, but in terms of the actual payload itself, all these protocols don't care what the payload is. It's just bytes of data to them, all the way through the whole stack. Whereas Bluetooth is much more structured than that. And that goes to show, Bluetooth in a way was a new way of thinking. It was say, let's get rid of all this stack and let's just focus on how to minimize inefficiencies that come along with this. So, we didn't even talk about stacks when I talked about Bluetooth Low Energy, right? I didn't mention eStack because it's its own stack, essentially. It's just one thing. It takes care of all these different things for you. And the benefit of this is that it's more efficient. You don't have the overhead of all these different headers getting layered on each other. It can also interpret the data better and know how to handle it. So it has plenty of advantages. It also has some disadvantages. Bluetooth Low Energy can't just connect to the rest of the internet without some kind of controller that maps a Bluetooth device, Bluetooth data into an IP packet, and up the chain it goes. It needs some kind of controller or some kind of gateway, whatever you want to call it, to convey that information and then send it up into the internet. So there's no way for the internet to reach down into a Bluetooth device. And that's, as far as I can tell, purposeful, because the internet is inefficient and it's hard to block communication with the internet. And so they want to isolate it and keep its own stack. There is research being done to see how you can add an efficient version of IP to Bluetooth Low Energy so it can just natively send out to the internet without having some kind of controller that has to interpret the data. So this is a really interesting difference between these two different protocols. And I want to just take maybe a slight tangent into this and dive a little deeper into the way this data is structured and talk about, I think, a very important topic called machine to machine, or M2M. I don't know if any of you have heard that before, but it's this idea that we want to be able to have machines talk to each other in a meaningful way without humans involved. And meaningful is the key word here. We can have machines talk to each other, they do that all the time, but how to make it meaningful and discoverable and take advantage of each other's capabilities without having a human have to manually program it to do take advantage of that capability. So another question along that lines is, how do you discover what each device is capable of? And that's a hard question. It usually involves a human to discover what it's capable of. Either you read some documentation or you look at an API or something like that, and that's how you discover, and then you program it to take advantage of those capabilities. Is packet structure enough? And it's not. Packet structure tells you how to arrange the data, but like I said earlier, the payload is just payload. It's just data. It doesn't tell you anything about the data itself. For this to work, you need structure throughout the whole system, not just this packet, but also in terms of the payload needs to have structure as well. Like I said, so you need a way of defining and describing the data itself. And I'm talking very abstract here. Hopefully that doesn't confuse you. And I'm not talking about any particular protocol. I will in a second. But I'm just saying in general, like, how do you describe data to each other that works for all data types, that works so that you can discover what kind of data is out there? And even fundamentally to that is, how do you discover what devices are there in the first place? Before you even get to the data, how do you know if a device is there and what data they have to offer you? So let me go through a kind of a silly example, just to hopefully get you on the same page with me here. So let's say you're building an application that tracks people's locations. I just made up this application. It could be anything, but you're just building an application that tracks people's locations. Well, you need some way to show a person's location on a map, right? So you're going to build an app. You need to have some map integration here so that you have a context of where these people's locations are. So the question is, how do you get this map information? And some of you maybe even built something similar to this before or used maps before, so you might have a very good answer to this. My answer is, well, you could use Google Maps API. That's common, or OpenStreet's API. Just some kind of API that offers maps. The thing is, though, that these APIs are very different. And hopefully you're familiar with APIs and what I mean by that. But it's a way of just calling out to HTTP and getting data back. But they're very different. The endpoints are different. The status codes are different. The data format's different. These two APIs are not interoperable. You can't just switch out one with the other. You have to write custom code that interacts with one API, and you have to write custom code that interacts with the other API. Well, shouldn't there be just one way to unify? If maps data is map data, why does it matter? Why does there have to be this different structure to it? Why can't there just be one way? And that's because machines aren't capable of reasoning like us humans are and writing custom code. There does have to be one way to do this, one way to get map data in order to enable machine-to-machine communication. So how do you describe your endpoints to an API so the machine can understand? Give that some thought. How would you do that? It's not that hard of an answer. You just have to be consistent is probably the biggest key, right? You have to be consistent between services, consistent between calls. How do you describe return values of an API so a machine can understand? Once again, that's not that hard either. We have HTTP status codes. That's machine readable. It can know what a 200 message is versus a 404 message. But you have to be consistent between all these different services, and that's where it can be hard. And just to take this API idea a little further, APIs are actually not the ideal case for machine-to-machine communication, but it's something that I think you're familiar with. At least I'm very familiar with. I use APIs for various things all the time, and so that's why I'm using it as an example. So one more example with this API stuff is there is efforts to try to standardize these APIs to make it easier to understand. So Swagger or Open API is an example of that. It's mostly tooling around how to describe an API. So let me click on this. So here's an example of a, call it Swagger or open API documentation, in terms of it's got all the capabilities of this API, along with what posting or putting. And if you click on it, you can see that you need an integer there, and specifically an int64. It gets passed in as form data. All the things you kind of need to know. It even has, some nice features in terms of you can try things out and test out things, and you can choose what kind of response code to get. So I'll show you an example of code that you'll get back, or the model in terms of what to expect in the return value. So this is a lot of tooling. It's a great thing. I'd be curious to know if you guys have ever used this. It's a pretty cool thing. I've used it a little bit for APIs I've built, but it's a more formal way of defining an API and try to standardize it across any API, so that you know what to expect. Okay, when I call this, upload image, when I post to it, I know I'll get back these 3 things, and I know code will be an integer, and I know type will be a string, and that way you can, it can work without any surprises. So let me switch back to the slides. So this is an example of what I mean of the step in the right direction, but it's not quite machine to machine. It's more about making it for humans, better for humans. And that's a great thing, but it's not quite machine to machine. So let me talk about another protocol that says it has machine to machine. This is CoAP. Have we talked about it before in class? I feel like we have, but maybe I'm mistaken. But it's a IoT protocol that's meant for constrained devices. It's in the name, Constrained Application Protocol. It's a really cool protocol. It's supposed to be like HTTP in terms of its semantics, so it has the same idea of a put and a get request and client server, and there's a status code that gets returned, and kind of a URL structure to it. But I highlighted here this idea of it's designed for machine-to-machine applications. So let's see what they've done to enable this machine-to-machine applications. So the first thing that they've done is they've defined a multicast address for device discovery. Now in this class we haven't really talked about multicast. It's just the idea that one device can send to multiple devices at once. It's not quite broadcast. It's not to everyone. It's only to some people. So typically how this is done is you subscribe to a multicast address. You say, I want to be part of this multicast group. You subscribe to this address right here that I've shown. And then if anyone sends that address, then you'll receive it. And so CoAP right there has an IP address designated for itself for discovery. So that means if I'm on a network, I could send a multicast request to that IP address, and in theory, if there's any other CoAP compliant devices on that network, they should respond to me. That's pretty cool to have that rendezvous point. That's I don't know why more people don't do this. So that's one way that makes for device discovery. Now we're not talking about data discovery here. We're just talking about device discovery right now. Just know if there's any devices out here in general. But then it does also define a way to format your data to have resource discovery or data discovery. So let me go through an example of what I mean here. It'll be easier to understand than the specification. So CoAP, once again, it has this multicast address. It also has a special request, a special URL, you can imagine, that every device should support. It's /.wellknown/core. So it means if you're a compliant CoAP device, that should be a defined endpoint for you. So I can just request this out on the multicast address. And what you should respond to with is some kind of status code. So that's how CoAP designs this 2.05. And then a list of all your endpoints that I can access. And it's a really strange structure, but in the angled parentheses, angled brackets, it's showing what the endpoint is, and then a semicolon, and then the content type. And it's trying to be very concise, and so it doesn't use it doesn't use ASCII characters very much. So content type 40 means it's an application/link format, which is what it is itself. What's returning is also application/link format. So if I go to /sensors now, I know what type of data I'll get back. So let's go do that. So I'll make another request to get /sensors, and I know what kind of data I'll get back. It'll be application/link format because it told me in the previous request. Okay, so I get back content, and this is what it gives me. So once again, same kind of format, but now it's telling me if I go to /sensors/temp, what I'll get back, the RT stands for resource type. The resource type will be temperature in Celsius. And the IF stands for interface description. So it's just a sensor. It's right here now we're able to discover. So if I were a device, and I didn't know nothing about your device, I could first go to the well-known /core, get back all the endpoints, and I could say, let me go to each of those endpoints and see what kind of resource type you offer me. I could go to the sensors, get back, say, okay, you offer temperature in Celsius. Great, I'm interested in temperature in Celsius. So now I know how to then get the temperature from your device. I go to /sensors/temp. It also offers /sensors/light. It tells you the unit of the light, it's lux, the return type, and it's also the interface type is a sensor. So now I know if I'm also interested in light, I can now go to that endpoint as well. So hopefully this is becoming clear of how you would architect this. Now I can write a program that does this automatically, discovers all your capability, and filters out and says what I'm interested in. So I'm interested in temperature. So if I see any resource type that has the word temperature in it, then I know I can then pull that data and get it. Or maybe I just want all the data you have to offer. And I can still reason about that because I know what the unit is for it. So this is a really cool idea here for the machine-to-machine, is that any device can discover any other device's capability without human involvement. But it requires really strict formatting. It requires to have discovery available. And these are things that aren't really followed. Everything kind of is its own custom solution. Each company wants to design their own custom approach or their own custom discovery protocol. And so there hasn't been really a unifying spec. CoAP is trying to be that. It hasn't really taken off very well, so I'm suspicious that it won't really work out. But for machine-to-machine to work, we need these things. And I think this is a key problem for IoT to solve, is if we want to have tons of these IoT devices around ourselves, we can't have a siloed approach where every company has their own design. We need some kind of standard or way of communicating. And just imagine that. You could walk into a home, or maybe a sensor comes into your home, and you could automatically know what that sensor is capable of doing. You wouldn't have to install any app. You wouldn't have to describe what it is. It could register itself with some kind of controller, and all of a sudden you'd just be able to get all the data back from that sensor, just all through the machine-to-machine discovery. I think that's a really cool vision, in my opinion. So that's my tangent for machine-to-machine. I think it's a really important problem that needs to be solved. No one's really going after solving it, or there's too many players in the game to really come up with a good solution that fits everyone's needs. Hopefully it'll happen someday. I think it'll have to for IoT to continue on. Okay, so I'll get off my soapbox about machine-to-machine now. And so let's cover the last thing about Bluetooth, and that's Bluetooth security. Kind of running out of time, so I don't want to go too deep into this. But Bluetooth has these two different modes for, or I call it security associations. There's the idea of pairing, which I think we should all be familiar with that word in the context of Bluetooth. But Bluetooth or pairing is actually a temporary secure association, meaning you set up the keys and now you can encrypt your data. But as soon as that connection is over, for whatever reason, you go away from each other or power cycle your devices or just times out, then that's no longer there. You have to repair again. So pairing is purely temporary. All the keys are stored in memory and they're not reused for later connections. So we call it pairing in Bluetooth Low Energy, but actually I think we mean bonding most of the time. Because I think that's typically what we do, is we actually bond our devices together. So bonding is the second part of pairing. So pairing is all you need to do, but if you want it to last longer, then you have to go to bonding. And so you pair, then you bond, and what you do is you establish more keys, and those keys are persistent and they're stored in memory in memory indefinitely. And this allows you to keep allows you to set up a connection faster in the future and keep that association between yourselves. So like when you turn on your Bluetooth headphones, they're bonded together because they just have to reconnect. They don't have to repair every time. So there's 3 ways to exchange keys with Bluetooth Low Energy. There's the Just Works method, which is really what it's called. There's the pass key, and there's out of band, OOB. So Just Works is the simplest and also least secure. All you do is you send the key that you're going to use in plain text over Bluetooth to the device, and you somehow come to an agreement of what key you're going to use. Oftentimes that key is just 0. That's kind of the simplest approach, is okay, key 0, and you still encrypt the data after you send out that key, but it's kind of useless, that encryption, because if you hear that pairing process, you can just look at the data and say, okay, I see the key is 0 or the key is some number. Now you can encrypt the data. So it doesn't actually protect you from very many attacks. It's susceptible to man-in-the-middle attacks. It's susceptible to brute force attacks because often the key is 0, and if it's not, it's kind of a small space to guess from. So this is not a great solution, but hey, it just works, I guess. So whatever. Okay, next is the pass key method. Trying to be a little bit more advanced, but still not much more advanced. So how it works is you have a key which is a 6-digit number, and this number is displayed somewhere on a screen somehow, and then you type it into another device. So I don't know if you've seen this. Where have I seen this? I feel like with my car audio system, when I was pairing my phone, I could be wrong on this, but I think when I pair my phone, the car audio system says, hey, type this number into your phone, some 6-digit number, and you type it in, and that's your key. And so that protects you against a man-in-the-middle attack if the attacker is not listening during the key exchange. But if there's someone listening during the key exchange, they still can't. It's still encrypted. They don't know what the password is. But because it's 6 digits, it's actually not that big of a number. It's not that hard to brute force it. So if you capture those frames, then you can just do a brute force attack on those frames until you guess the right number, and then from there you can now decrypt the data. So it's better than Just Works, but it's not that great either. And that's often why Bluetooth is so broken. It's security. There's a lot of, and I'm only highlighting a few examples of ways you could defeat Bluetooth security. There's a lot of other ways to do that. And so, but it makes sense for the context of Bluetooth, because I could imagine them thinking, well, we're not going to do pairing very often. And you're probably not going to be pairing in an environment where you're worried about an adversary, listening in. Whether that's true or not, you could see why it wouldn't maybe matter if someone's listening when you're pairing, because you're not pairing that often. You do it maybe once in the lifetime of your Bluetooth headphones, and so just make sure you do that privately in your own home, and then you're fine. So I could see why they're okay with this. They're trying to make Bluetooth Low Energy very lightweight and efficient, and so they don't want to bother with a lot of these details. I'm sure with Bluetooth 5, they've addressed a lot of these things to make it more secure, because Bluetooth is that much more popular. But I could see why they would choose this approach. Okay, the last approach is the out-of-band communication approach. So what I mean by this is that you just kind of punt and say, we're just going to use some other protocol to send that key. And then that way, the key is never sent, encrypted or otherwise, between these two devices. And so this is the most secure approach, because you're actually relying on an out-of-band communication protocol. So here I have an example of an NFC. So you can imagine you have some Bluetooth device. The way that you set the security association is by scanning an NFC tag, and that has the key that's programmed into the device. So you're transporting that key through NFC, not through Bluetooth itself. So, of course, if the out-of-band communication you're using is not secure, then it doesn't provide any very good guarantees, but it does make it harder. Now, as an attacker, I can't just set up a Bluetooth sniffer. I have to have some other protocol to sniff as well, so NFC, and that's harder to do. And so this is the most secure because you're not actually exchanging keys through Bluetooth itself. You're doing it through some other means. Okay, so that's it for Bluetooth, low energy. Hopefully you've learned some stuff. I really, think about, I'm sure you're going to spend a lot of time thinking about this lecture, right? Because you guys do that all the time. But if you do think about it, think about the differences between Bluetooth and Wi-Fi. We spent a lot of time talking about Wi-Fi. We'll only spend this lecture, talking about Bluetooth, low energy. So think about, why did they choose the things that they chose? And it starts making sense, going back to those knobs of data rate and all these things. And there's more knobs we haven't talked about in terms of security and the characteristics of the topology. But think about those things and why Bluetooth chose the way it did, and maybe how you would design a protocol that would maybe be a hybrid of those two, or be even more efficient than Bluetooth low energy. And we'll be talking about a few other wireless protocols, Zigbee and LoRa, that turn other knobs in other directions and produce other types of protocols. So thanks for listening, and like always, comment if you have questions, message me on Slack. I'm available during office hours, so please reach out to me anytime, and I'd love to talk to you. Okay, thanks.